Your morning routine is 2,000 years old. The bristles on your toothbrush, the paper in your bathroom, the cash in your wallet. You've already used all three today, and none of them came from the modern world. Chinese engineers solved these problems so well that later ages mostly changed the materials, not the underlying ideas. 15 inventions, still in your hands, still in your home, still running your day. Stay until the end. Number 1 is the invention that gave the entire world its heartbeat, and almost nobody knows where it came from. We think we live in the most advanced time in human history, and in many ways we do. But here's what the history books quietly skip over. The tools you reach for every morning, the ones so ordinary you've stopped seeing them, many were built during Chinese dynasties that rose and fell before many European cities had anything close to modern sanitation or reliable clean water systems. From the Han to the Song, Chinese engineers were solving the same problems we still face today. How do you stay clean? How do you feed millions of people? How do you move heavy things with less effort? How do you find your way when the stars disappear? How do you know what time it is? They answered every one of those questions, and their answers were good enough to last 2,000 years. This isn't a history lesson. Every invention in this video is physically in your life right now. Some are in your kitchen, some are in your pocket. One of them is ticking somewhere in the room you're sitting in. Let's start where your day starts, in the bathroom, with something you put in your mouth every single morning. Think about the last time you actually looked at your toothbrush, not just grabbed it, but really looked at it. The rows of bristles, the angled head, the handle shaped to fit your grip. It feels like it came off a factory line last week. It didn't. Before the Tang dynasty solved this problem, people cleaned their teeth with chew sticks. You'd gnaw on a twig until the end frayed into something rough enough to scrub with. Others used linen rags dipped in salt. It worked the way wiping a window with a wet sock works. Technically, not well. Tang dynasty craftsmen changed the whole approach. They took hog bristles, stiff, durable, and naturally tapered at the tip, and anchored them into handles carved from bamboo or bone. The bristles were set in rows, spaced to flex between teeth, angled to reach the back of the mouth. This wasn't a rough attempt at a brush. It was a tool built around how the human mouth actually works. Chinese travelers carried these along the Silk Road in small leather pouches. Portable, personal. Already being made in large numbers, while medieval Europe was still debating whether bathing too often was bad for your health. The modern toothbrush industry is worth over $8 billion a year. The bristle angle, the row spacing, the handle length, the engineering logic is the same. We swap bamboo for plastic and hog hair for nylon. The solution hasn't changed in 1400 years because it didn't need to. Now that your mouth is clean, let's move to the other side of the bathroom, where China solved a problem the rest of the world ignored for another 1,000 years. In 589 AD, a Chinese scholar named Yan Jitui wrote something that tells us more than he probably intended. In a personal essay, he noted that he refused to use paper printed with the words of wise men for, and this is a direct quote, toilet purposes. He wasn't announcing a new invention. He was writing an etiquette rule about an existing habit. Paper in the bathroom was already so normal that someone felt the need to set guidelines about which paper was acceptable. That's the detail worth sitting with. Not that toilet paper existed, but that it was common enough to need rules. By the 14th century, it had grown into something much larger. Imperial records describe hundreds of thousands of sheets produced every year just for the royal household, cut to specific sizes, stored in dedicated rooms, managed like any other essential supply. This was an organized hygiene industry running at scale. Meanwhile, the rest of the world was using stones, sea sponges on sticks, corn cobs and leaves. Europe wouldn't commercially produce toilet paper until the late 1800s. China had been running this system for over 1,000 years before that. The global toilet paper market today is worth more than $100 billion a year. That entire industry traces back to a habit so ordinary in 6th century China that a scholar was already writing rules about it. From the bathroom to the kitchen now, where one piece of curved metal changed the way the world cooks. Here's a question worth thinking about. Why does food cooked in a wok taste different from food cooked in a flat pan? Same ingredients, same fire, different result. The answer is physics, and the Chinese worked it out centuries ago. A wok's walls are thin enough that the metal reacts to heat almost instantly. Turn up the flame and it's scorching in seconds. Pull it back and it cools just as fast. That speed gives the cook a level of control that a heavy, thick-bottom pan simply can't match. The curved shape does something else. It creates two cooking zones at the same time. The center, sitting directly over the flame, gets hot enough to sear meat in seconds. It produces that slightly charred, smoky flavor that professional chefs call Wok Hei, the breath of the wok. The sloping sides stay relatively cooler, so a good cook is constantly tossing food between the scorching center and the gentler edges to keep everything cooked through without burning. One pan, multiple temperatures, all controlled with motion and flame. This design came from a very practical problem. Wood and charcoal were expensive. Fuel wasn't something you wasted. The wok was built to pull maximum cooking power from minimum fire. A small bundle of straw could produce a full meal. That efficiency wasn't a side effect. It was the whole point. Professional chefs around the world have been going back to woks in recent years, not out of tradition, out of results. The shape outperforms most modern cookware for high heat cooking, because the people who designed it already found the best answer. A wok is useless without fire though, and for most of human history, starting a fire was slow, frustrating work, until China made it instant. Picture a night market in Song Dynasty Kaifeng, over 1 million people living in one city, the largest on earth at the time, street vendors lighting their stalls, cooks firing up their grills, families starting their evening meals, all of them reaching for the same small object, a wooden stick tipped with sulfur. Touch it to a hot coal. It catches immediately. No flint, no steel. No 10 minutes of frustrated work in the dark. Fire in one motion. Records from the 10th century describe these being sold openly in markets across Chinese cities. They were a household item, bundled and bought the way you'd buy candles or salt. The idea was simple. Sulfur catches fire at a low temperature, so a stick coated in it only needs brief contact with an existing heat source to light up. You still needed a coal or ember to start the reaction, but it turned fire starting from a skill into something anyone could do in seconds. The modern strike anywhere match didn't appear in Europe until the 1820s. China had portable, fast-lighting fire sticks nearly 1,000 years before that. The chemistry got more refined over time. The core idea, a small object that produces fire quickly and reliably, was already a solved problem in a Song Dynasty market. Fire cooked the food, but growing enough food to feed an empire of millions that required a machine that changed the ground itself. Two farmers, same field, same ox. One of them finishes in half the time with soil that's better prepared and ready to plant. The difference between them isn't strength. It isn't experience, it's the shape of a blade. A straight plow drags through dirt. It cuts a line, but the soil stays roughly where it was. Packed down, unturned, resistant. The ox strains. The farmer strains. The ground barely moves. A curved moldboard plow works differently. As the blade passes through the soil, the curve lifts it, flips it over, and lays it back down in one smooth motion. The earth turns itself. The resistance drops. The ox pulls less. The farmer covers more ground, and the soil left behind is loose, full of air, and ready for seeds. Chinese smiths cast these blades in iron, not wood, not bronze, which meant they stayed sharp through heavy clay soils that would have destroyed a wooden plow in a single season. The curved shape, combined with the iron material, made this one of the most effective farming tools ever built. This design eventually moved west along trade routes. When similar curved iron plows appeared in Europe, they helped drive medieval agricultural expansion. Historians connect the moldboard plough directly to the agricultural growth that fed Europe's expanding population through the Middle Ages. Modern tractor ploughs, the ones working fields right now, still use this same basic curved geometry. 2,000 years of farming technology looked at this design and kept it, because nothing better came along. Turning the soil is one thing. Planting seeds with precision, so none are wasted, none are eaten by birds, and everyone lands at the right depth. That's a different problem entirely. Scattering seeds by hand is an act of hope. You throw them out, the wind takes some, birds take more, and whatever reaches the soil lands at random depths, some too shallow to survive, some too deep to sprout. It's farming as a gamble. The Han Dynasty engineers looked at that process and decided it wasn't good enough. The machine they built was the world's first precision planting tool. A hopper on top holds the seeds. Below it, multiple tubes run down to the soil at even intervals. As the device moves forward, pulled by an ox, seeds drop through the tubes at a steady, controlled rate. They land in neat rows at a consistent depth. A blade behind the tubes covers them with soil immediately, before any bird has time to react. 3 problems solved in a single pass. Even spacing, correct depth, protection from the moment of planting. Every seed had the best possible chance of becoming a plant. Europe didn't build a comparable multi-row seed drill until Jethro Tull's design in the early 1700s. That's roughly 1800 years after the Han Dynasty was already using this technology to feed cities of hundreds of thousands of people. When historians talk about the agricultural revolution in 18th century Europe, they're describing the moment Europe caught up to something China had already solved nearly 2 millennia earlier. More food meant more trade. More trade meant bigger transactions. And carrying 100 pounds of iron coins on a donkey across a mountain range was nobody's idea of a good system. In 10th century Sichuan, merchants had a weight problem. Iron coins were the standard currency. They worked, but they were heavy, genuinely, physically heavy. A large purchase didn't require a purse, it required a cart. Merchants travelling between cities were moving small fortunes in metal across difficult roads, which made them slow, expensive to operate, and an obvious target. The solution that came out of this was simple and elegant. Merchants started depositing their coins with trusted shops and receiving paper receipts in return. Notes that represented the value of the metal sitting safely in storage. The paper travelled, the coin stayed put. Commerce moved faster with far less risk. The government saw what was happening and made it official. The result was the Jiaozi, the world's first government-backed paper currency. Printed, regulated and accepted across regions because a central authority stood behind it. The paper itself had no real value. The trust behind it was everything. That is the exact principle behind every banknote on Earth today. The bill in your wallet isn't valuable because of the paper it's printed on. It's valuable because a government says it is, and enough people agree. The Song Dynasty built that agreement. We've been running on it ever since. Every dollar, euro, pound and yen in existence is a direct descendant of a 10th century Chinese merchant handing over a piece of paper instead of a cartload of metal. Moving money got lighter, but moving heavy cargo, stone, grain, weapons, still required muscle, unless you knew where to put the wheel. The wheelbarrow looks too simple to be interesting. A wheel, a frame, 2 handles. What's the insight? The insight is where the wheel sits. Put the wheel at the front of the frame, which is how many Western designs work, and the person lifting the handles carries roughly half the load with their arms and back. The wheel helps, but the human is still fighting gravity on every step. Put the wheel directly under the load, the Chinese design, and the physics shifts completely. The wheel carries almost everything. The person behind it provides balance and direction. Their legs walk, their arms guide, the weight stops being their problem. That difference sounds small until you're moving 300 pounds of rice up a narrow mountain trail. Then it's the difference between one person finishing the job and 4 people struggling with it. Military tradition links the center-mounted wheelbarrow to Zhuge Liang, the strategist of the Three Kingdoms period, who reportedly used devices called wooden oxen to move military supplies through the mountain passes of Sichuan, terrain where pack animals struggled and carts were useless. Whether Zhuge Liang personally designed them or not, the military use was real. Supply lines that once needed animals could now be run by individual soldiers, each moving far more than they could carry on their backs. The center-mounted wheelbarrow is mechanically a better design than most wheelbarrows sold in hardware stores today. The ancient engineers found the right weight distribution. Physics doesn't care what century you're in. From mountain trails to open water now, where catching dinner required a machine most people assume was invented somewhere in England. A large fish on a handheld line is a tension problem. Pull too hard and the line snaps. Give too much slack and the fish is gone. The angler needs to apply steady, calibrated resistance. Enough to tire the fish, not enough to break the connection. Doing that with bare fingers wrapped around a line is exhausting and imprecise. One wrong move and the fish wins. The fishing reel solved it mechanically. A spool with a crank handle lets the angler release line under controlled tension when the fish runs, then pull it back steadily when the fish tires. The drag system, a mechanism that lets the spool spin against resistance, keeps the line from going too slack or pulling too tight. The machine manages the tension. The angler manages the timing. Chinese paintings from as early as the 12th century show anglers using reel-equipped rods on rivers and lakes. The components in those paintings, spool, crank, line guide, are the same basic parts on every fishing reel made today. Recreational fishing is now a $50 billion global industry. The reel is the centerpiece of every rod sold in every sporting goods store on Earth, and the core mechanics of that reel were worked out on Chinese rivers 800 years ago. Once you're out on open water, catching fish is one thing. Finding your way home, especially when clouds cover the stars and the coastline has disappeared, is a different problem entirely. It didn't start as a navigation tool. That's the part most people don't know. The earliest Chinese magnetic device was a south-pointing spoon, a piece of lodestone carved into the shape of a ladle, polished smooth on the bottom, set on a flat bronze plate. When you placed it down, it rotated until the handle pointed south. Every time, without fail. This wasn't used on ships. It was used by geomancers, practitioners of Feng Shui, to align buildings and tombs with the Earth's magnetic field. The compass was invented to arrange spaces in harmony with invisible natural forces. Navigation came much later, almost as an afterthought. By the 11th century, Chinese sailors had refined the idea into something built for open water. A magnetized iron needle, floated in a small bowl of water on a ship's deck, held its direction regardless of how the vessel moved. For the first time, sailors could hold a course in total darkness through thick fog, without a single star visible overhead. Every other maritime culture in the ancient world anchored and waited when the sky closed over. Chinese merchant vessels kept moving. They arrived days ahead of everyone else. They opened trade routes that reshaped the ancient economy. This technology spread along those same routes, to Arab navigators, then to European sailors, and it made the age of exploration possible. Every voyage of discovery in the 15th and 16th centuries was guided by a tool that started as a way to align a building with the Earth's energy. You can navigate through fog now, but what about rain? A sudden downpour on the road and you need something that folds small enough to carry but opens wide enough to keep you dry. The canopy isn't the invention. Anyone can stretch fabric over a frame and hold it above their head. That's not engineering, that's a tent on a stick. The invention is the joint. The hinged rib system, the mechanism that lets an umbrella frame fold inward and collapse into a compact, portable size, is a real mechanical achievement. Each rib needs to pivot at multiple points, lock open under load and release cleanly when you want to close it. Getting that geometry right in bamboo and early metalwork took genuine engineering thought. Chinese sources from as early as the 1st century CE describe carriage umbrellas with extendable and retractable frames, canopies that could be opened over a passenger and folded away again when no longer needed. The hinged rib design that made this possible is, in its basic geometry, the same mechanism in the umbrella by your front door right now. The canopy itself was oiled or lacquered paper stretched over bamboo ribs. Lightweight, genuinely waterproof. Durable enough for daily use on long journeys. This wasn't a ceremonial object kept for special occasions. It was practical weather equipment, used and carried the way you'd carry one today. 2,000 years of material science gave us fiberglass ribs and nylon fabric. The folding joint geometry, the part that actually makes an umbrella portable, hasn't needed to change. You can stay dry in the rain, but what happens when the ground itself starts to move, and you need to know about it before the shaking reaches your city? In 132 AD, a bronze vessel sat in the imperial court of the Han Dynasty. Roughly 6 feet across, shaped like a wine jar, 8 dragon heads ringed the outside, each one holding a small bronze ball in its jaws. Below each dragon, an open-mouthed toad waited on the ground. The court officials who walked past it every day probably saw it as an impressive piece of decoration. Then one day, without any warning, one of the balls dropped. It fell from a dragon's mouth and landed in the toad below with a clear, ringing sound. The dragon was pointing northwest. No one in the capital had felt a thing. No tremor, no shaking. The officials were skeptical. Some were openly dismissive. Zhang, the engineer who built the device, said nothing. He waited. Days later, a messenger arrived from the northwest, covered in road dust, carrying news of a devastating earthquake that had struck hundreds of miles away. The device worked through an internal pendulum. A heavy mass suspended inside the vessel would swing in response to ground movement too faint for human senses to detect. When it swung, it triggered a lever that released the ball on the matching side, pointing toward the source of the disturbance. Modern seismographs use digital sensors and satellite networks. But the core idea, detecting ground movement at a distance and identifying its direction, was working in a bronze vessel in 132 AD. The Western world wouldn't attempt anything like it for another 1700 years. Zhang listened to the surface of the earth. In Sichuan province, other engineers went further. They drilled straight down into it, deeper than anyone thought possible with the tools they had. The modern oil industry traces its beginning to 1859. Edwin Drake, a well in Pennsylvania, 69 feet deep. The first commercial oil strike in America. That's the story most people know. Here's the part that gets left out. During the Han Dynasty, workers in Sichuan province were drilling wells to depths of around 140 meters, nearly 460 feet, using iron drill bits attached to long bamboo cables. They weren't looking for oil. They were drilling for brine, salt water, and for the natural gas that sometimes came up with it. The method was called percussion drilling. A heavy iron bit was raised by a team of workers and dropped repeatedly onto the rock below, chipping away at it stroke by stroke. The bamboo cable absorbed the impact and carried the force downward. As the hole deepened, bamboo casing was lowered in to keep the walls from collapsing. It was slow, steady, and it worked. When they hit a gas pocket, they didn't let it go to waste. They piped the gas through bamboo tubes to the surface and burned it under evaporation pans to boil off the brine and produce salt. An integrated energy and extraction system powered entirely by what came out of the ground, running 2,000 years before the first oil derrick. The modern petroleum industry uses the same basic principle, a heavy bit striking rock repeatedly to go deeper. The scale is different, the materials are different. The concept is the same one Sichuan salt workers were using during the Han Dynasty. Edwin Drake's famous well in 1859 was 69 feet deep. Chinese workers had drilled to nearly 7 times that depth 2,000 years earlier, with bamboo and iron. We've gone deep into the earth. Now let's go up into the air, with a toy that became the ancestor of one of the most important machines ever built. Around 320 AD, Chinese children were playing with a toy that held, without anyone fully realizing it, one of the most important principles in the history of flight. The Bamboo-Copter is simple. A stick with angled blades at the top. You spin it fast between your palms and let go, and it rises into the air. The angled blades push air downward as they spin. The reaction force pushes the toy upward. This is rotor lift, the same physical principle that keeps every helicopter in the sky. A child's toy, working rotary flight in the 4th century. 1500 years later, Sir George Cayley, one of the founding figures of aeronautical science, built a larger version of the same toy in his English workshop. He measured the lift it produced. He wrote papers on what he observed. Those papers fed directly into propeller theory, which fed into the first powered aircraft, which fed into the helicopter. The line from a bamboo toy in 4th century China to a modern helicopter rotor is not a loose comparison. It's a documented chain of influence in the history of aeronautical engineering. Every helicopter flying today, every drone, every ship's propeller, every ceiling fan works on the principle that a spinning angled blade moves air and generates force. That principle was demonstrated in a children's game in ancient China, centuries before anyone in the Western world thought to ask why the toy went up. We've covered your bathroom, your kitchen, your wallet, your fields, your oceans, and the sky. But the biggest invention, the one that quietly controls every single minute of your modern life, is still ahead. Find a quiet moment and listen. If there's a mechanical clock nearby, a wall clock, a wristwatch, anything with moving parts, you can hear it. That soft, steady tick, 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 equal intervals, perfect rhythm. Time cut into identical pieces. That sound has a name. It's called the escapement, and it is the most consequential mechanical invention in human history. Here's the problem it solves. A clock needs a power source, a falling weight, a coiled spring, a flow of water. Left alone, that power source releases all at once. A gear driven by a falling weight doesn't tick. It spins freely, fast at first, then slower, then stops when the weight hits the ground. Useless for measuring time, the escapement catches the gear. It holds it for a precise, controlled moment, then releases it to advance exactly one tooth, then catches it again, holds, releases, one tooth at a time, at perfectly equal intervals. It takes continuous, uncontrolled energy and breaks it into measurable steps. It turns a spinning wheel into a clock. Around 725 AD, a Buddhist monk and engineer named Yi Xing was building a water-powered astronomical clock for the Tang Dynasty court. Water flows continuously, smooth, unbroken, impossible to count. Yi Xing's solution was a mechanism that caught the water's energy in equal portions and released it in controlled steps. It was the first documented escapement mechanism in history. In 1088, the engineer Su Song built on that foundation with a clock tower in Kaifeng that stood several stories tall, a rotating celestial globe, automated figurines that marked the hours, a sophisticated mechanical escapement driving the entire structure. It was a mechanical system for tracking the movement of the heavens, and it worked. Most people believe the mechanical clock is a European invention from the 1300s. The escapement, the core technology that makes a mechanical clock possible, was built in China in 725 AD, nearly 600 years earlier. And here's what that means for your life right now. The escapement didn't just measure time, it made time something people could organize around. It gave humanity the ability to coordinate, to schedule, to synchronize at scale. Trains run on time because of it. Factories run in shifts because of it. Your phone syncs to a global time standard that traces its mechanical ancestry back to Yi Xing's water-driven gears in 8th century China. Every structured hour of your day, your alarm, your meetings, your deadlines, your sleep, exists because a Tang Dynasty monk figured out how to catch a gear tooth and hold it for exactly the right amount of time. 15 inventions. Every one of them is in your life right now, in your bathroom, your kitchen, your wallet, the clock on your wall, the sky above your head, and the ground beneath your feet. Ancient China wasn't building for its own era, it was building the foundation for ours, and we've been living inside that foundation ever since, mostly without knowing it. If that's the kind of history you want more of, the kind that changes how you see the ordinary things around you, then hit subscribe and come back for the next chapter, because the ancient world built far more than this, and we're just getting started.